And now I can share. So sadly, here's my problem. This thing won't sync. I have all the notes, except they're all written up ahead of time, which is not exactly what you want. So maybe we'll kind of try switching between them since that's the only way to see them. Okay. So I'll try to write them out for you. Okay. So we're working on digital logic circuits today. Okay. And so the main idea is that there's basically a correspondence between logical circuits and uh, truth tables, okay, or kind of logical statements. Ooh, it finally synced. Okay, good. Okay, so you can design and analyze um, digital circuits using logic. Okay, which I mean seems like not the world's most astute observation, but you'll see how much correspondence there is and how some of the tools that we've been working with in transforming digital circuits can, in transforming logical statements, can be used to actually simplify circuits, which is a pretty cool thing. A very cool thing. Okay, so let's consider some circuits. So the first example is we're going to have a battery, which is basically 4 lines, okay? And then we're going to have a circuit. And we're going to have 2 kind of open things here, 2 switches, okay? And then a light bulb. And then we're going to close the circuit, okay? So the idea is that if that circuit is closed, there's current flowing from the battery through the light bulb, and then there's a light, right? And so to close this thing, we would need to move one of these switches, or I guess both of these switches, down to kind of connect, right? And we can think of these as P and Q, switches P and Q, okay? And so based on this, we can kind of analyze the circuits in terms of P and Q, and let's call the bulb B, okay? And B. All right, so when P is closed, okay, and Q is closed, okay, is the bulb on or off?
Off.
Well, it actually would be on. Thank you. Flow
Is
from
on represented by true in traditional logic, or would that be by false?
uh, you know, it's kind of arbitrary. You can assign it to however you want. But let's go with true because it's going to be easier, right? So if these things are closed, then there's current flowing all the way to the battery, and the bulb is going to shine, right? So on the other hand, so this would be on. Okay? On the other hand, if let's say P is closed, but Q is open, okay, the bulb would be off, right? Because the circuit is not closed as a whole. Okay? And then you can kind of analyze what happens. Well, if P is open and C is closed, well, this is also going to be off, right? And if, let's say, both of these are open, right, you can say that the bulb is not on and kind of label this as false. Right, so you can kind of get to different, correspondence. You use different symbols that have some meaning in the context of the problem. The underlying logic is going to be the same. All right, so let's consider another circuit, which will also start with the battery, okay? And then what we're going to do is we're going to split that circuit in half here, have 2 switches, and then we're going to join, and then we'll put the light bulb, and then we're going to close it, okay? So we'll call this P, and we'll call this Q. Okay, so what does this table look like for the circuit? Okay, so let's say that P is closed and Q is closed. Okay, is the bulb on or off?
On.
On, thank you. Okay, so that's going to be on. Let's just call it true. Okay, and if this is closed and this is open, is the bulb on or off?
On.
On. It's also on, right? The only way that it's going to be off is if neither P or Q is closed, right? And so you can think of this as being basically the circuit for P and Q, and this being a circuit for P or Q, right? If you replace closed with true and open with false, you'll see that we're exactly getting to the truth tables for these two functions.
Would these then be P and Q and P or Q, and then the arrow to B?
Not exactly. So let's do a comparison, right? So let's say we have, let's do a P and Q in terms of true and false. Okay, and then we're gonna do P or Q. Okay, which will be true, 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 false. Okay, you can then see that the behavior of the bulb corresponds to the behavior of P or Q. Those are kind of equivalent in some sense, right? And so you can, look at the bulb as the output, but it corresponds to the function that is implemented by the circuit.
Oh, I
Does
see.
that help?
Yeah. So I guess like what you're sort of saying is that B isn't. If you set it to be the arrow, then it would be evaluating if those happen, if B then happens.
Right.
But
Correct.
B is actually just essentially the value of the output, not a part of
Exactly.
the equation. I see.
Exactly. Exactly. Yep. Yeah, that's a good way of thinking of it. It's the value of the output, right? And so, since 40s and 50s, we're looking at start looking at vacuum tubes. Well, actually before that, but vacuum tubes started being used in 40s and 50s for digital computers. We started to have transistors a little bit later on, and those circuits still can implement things like P and Q and P or Q, except the difference is that instead of having kind of voltage or no voltage, you would have high voltage or low voltage that would be used to represent 1 and 0. Right, so logically they're the same, they're just implemented a little bit differently to work. Instead of using on-off, they will work on high and low voltage. So that's just kind of worth mentioning in relation to how modern since the 40s computers work. Okay, so let's consider circuits. Okay, where we're gonna have inputs P, Q, and R. Okay, and we're gonna have a circuit which is a black box, and out of it we have some output S. Okay, and I'm going to tell you that this is the behavior of the circuit. P, Q, and R, and then the output S. Actually, you know what? I'm going to rewrite this. Let's rewrite this in ones and zeros. Start getting used to that notation. Okay. And I'm going to tell you that the output of this is 1, 0, 0, 1, 0, 1, 0, 0. Okay. And there is some set of some circuitry inside that box that behaves like this. Right? The question is, what is that logic? Can we tell what it is? Can we design a circuit that implements this particular output S based on the inputs P, Q, and R? Okay, so let's jump into this. So first of all, circuits are composed of gates. Okay, so we can have different types of gates. We'll start with the NOT gate, okay, which will look like this. Okay, it's a triangle with a circle after it, and then we get the output R. Okay, and so the behavior of this will be, this is an R, okay, 1, 0, 0, 1. Okay, you put in P with let's say high voltage of represented by 1, and the output of that circuit going into R will be low voltage represented by a 0. Okay. When we simplify this, we can simply draw this as a triangle with a dot. You don't have to write and inside it. And these are basically symbols. Okay, we can then have another type of gate, okay, which will be the AND gate. Okay, so that's a kind of straight line here, and then a sort of a rounded box. Okay, 2 inputs, P and Q, and then an output, which will be R. Okay. And the behavior of this is going to be 1, 1, 0, 1, 0, 1, 0, 1, 0, and the output of this is going to be 1, 0, 0, 0, right? Which basically corresponds to P and Q. Okay, and then a final gate that we care about for now is going to be P and Q. Okay, and this one is drawn as kind of a half moon here, and then these come to a point as opposed to being rounded in the end. Okay. And so we have 2 inputs here, P and Q, and logically this will behave as P over Q. Any questions?
So does 1 correspond to true and 0 corresponds to false?
Yes.
Right.
Mm-hmm. Okay, let's build a circuit. So, have an example. All right, so we have P and Q, and I'll do this, and then this. Okay, and we get R. All right, so if I give you this circuit, and I tell you that the input of P is 0, and the input of Q is 1, what is the output R?
1.
1. That is correct, right? So we have P input 0, it goes through a NOT, so this becomes a 1. Q doesn't change, it is a 1. This is an AND gate, and so the output is 1. Okay. And so this circuit will behave in the same way. Okay. Actually, let me draw this out. Okay, so we can have P and Q with different inputs, right? All the combinations. And the output of the circuit is going to be not P and Q. Okay, so when the input of when P is 0 and Q is 1, the output is 1. Otherwise, the output will be 0 on any other inputs. Okay, so any questions? Okay, let me show you guys another example then. So let's say that we have this circuit. All right, we're going to say P, space this out a little bit, Q, and then R. Okay, and the circuit looks like this. Okay. What logical expression does this circuit represent? Right? This gets a little trickier. We have more gates here. We need some method for analyzing this. Okay? So the first thing we can do is understand that this first gate connecting P and Q is an OR gate. So the output of this, change colors. The output here is going to be P or Q. Okay, makes sense? Then we have a NOT gate, so the output of that is going to be not the input, and the input is P or Q. Okay, and then we have an OR gate with R, so the output here is going to be not first input and second input. Okay, so you can kind of trace a circuit and build up the logical expression that it represents.
Can I ask a question?
Yeah.
Why is the final gate that's closest to S is an AND gate?
It's an AND gate, yes.
Isn't it OR? Because that shapes like the triangle.
So the way to read those is that, and this kind of the right side of it is going to look something like this either way, right? If you're going quickly, right? But if it's an AND, this will be a bar. If it's an OR, this will be concave. That's how you can differentiate the two.
Okay, I see. So it looks similar, but it's different. That's why
Yes.
I just mix up OR and AND
Yeah.
gate. Okay.
Mm-hmm. Yeah, if you look in the book, you can see like the really nice symbols. But when you write those quickly, they kind of start looking like each other, and so you differentiate based on that first line. Okay. All right, let's do a let's see. Okay, let's do a quick exercise. I think we have time, which is exciting. All right, so I would like you guys, let me actually do a new page. Okay. To build a circuit for not P and Q for not Q. All right, I will give you guys 3 minutes for this. Ask questions if you need to.
Can I ask a question?
Yeah.
Is it or not Q, or is it or not R?
Or not Q.
Okay, so there are two Q inputs.
Yes.
Okay.
All right, so let's look at the answer for this. Okay, see what you guys have. So we have P and we have Q. Okay, actually I'll space this out a little bit. Okay, so we have two inputs, and the first thing we're going to do is create a NOT for the P. Okay, and then we can have an AND gate. Okay, that combines NOT P and Q. Okay, and now we want to also to OR it with NOT Q. So we can split this wire here, put in a NOT gate, put in an OR gate, and feed it like this. Okay. So this starts being a bit more complicated. We can start doing different things here. So maybe we should talk about the rules for building circuits. Okay. So first, don't combine wires. Okay, so if you have, let's say, some input and some other input, okay, you cannot do this. Okay, that's bad. If you have an input and an input, you can have some gate, and then you can combine them, right? So there's no combining wires directly. But you can split wires. Okay, so if you have a Q, this is perfectly okay. We can definitely do this. We can do the split. That is okay. Okay. So use output as input. Okay, so we have, let's say, some gate, and then that's going to be, this is, the output of this gate is going to be the input to the next gate. Okay, and then finally, the last one is don't create loops. Okay, so if you have something, let's say a gate, okay, and then a whole bunch of other things, but you don't want to then feed the wire like this. Okay, that's bad. All right, so once you have input, it's got to be a tree, right? You can't have any cycles in this, at least not between gates.
Can you give us an example of using the output as input incorrectly?
Yeah, sure. So, I mean, this is kind of an example, but maybe it's confusing. So let's say, okay, let's say we have, I don't know, this is kind of like a nonsensical example, but I will try. Okay, so you have something like, I don't know, this, right? And then the output of that NOT is being fed as the input into this gate. Right? It's not clear what the circuit even does. Right? There is actually no output from it. Right? I mean, you could say that there is an output here, right? Where, I don't know, there's a NOT gate, whatever, and that's your output, you know, R. Right? I'd be fine, but the circuit, we can't reason about it. Right? So you could build it and electricity would do whatever it does, but now we have a loop that we can't reason about, at least not with the tools we have.
Maybe I'm just not understanding with the previous one. Use output as input. I'm not thinking.
Yeah.
How could you do
Yeah,
that
sure.
differently?
To the next gate. Okay, so this is output, and this here then becomes input.
Yeah, I understand that. I just don't understand what other options there are. How could you not do that? Is it just the rule? It's just how it works. It's not a.
Yeah.
There's not a bad
Yeah.
example. That's just how you do it.
Yeah, that's just how you do it.
Okay.
Yeah. Okay, so let's do the last thing, which is hopefully we have enough time for this. Okay, so let's go back to our example where we have a black box. Okay. So we had a black box, which gave us these properties. Okay, we had P, Q, and R, and they are the inputs to some circuit board. Okay, and then we have an output S. Okay, great. And I'm going to tell you that. Actually, let's give ourselves some more space here. Okay, that this behaves like this. Okay, so the output is going to be 1, 0, 1, 1, 0, 0, 0, 0. Okay, I think actually that might be a little bit different from the first page. So let's go by this. Okay. Okay. So how do we figure out what does the circuit do and how can we design it? Okay. So first thing we're going to do is we're going to construct a conjunctive expression for all 1 outputs. Okay. That produces zero for all other inputs. Okay, this is a bit confusing, but there's a very clear example. Okay, we have 3 1 outputs here, right? For each one, we're going to construct a conjunctive expression, meaning using ands. So this is going to be P and Q and R. Okay, so S is 1 when P, Q, and R are all 1. Okay, for this row, we're going to say that S is 1 when P is true, okay, and Q is false, and R is true. And then for this one, we're going to say P is true and not Q and not R. Okay, and you can see that, let's look at the first expression, P and Q and R. It's only going to be true when all these things are 1, right? It's going to produce 0. This expression is going to produce 0 for all other inputs, right? And the same is true for the other expressions. Okay, so now 2 create a disjunctive normal form. Okay, what that means is that we're going to take our conjunctions, P and Q and R. We're going to OR it with P and not Q and R, or P and not Q and not R. Okay, that's called a disjunctive normal form. Right, you have in parentheses conjunctive things that are linked by disjunctions. Okay, and based on this, we can build a circuit. Okay, so we have our 3 inputs, P, Q, and R. Okay, and we can build the first expression, okay, which will be an AND gate taking all 3 inputs. Okay, so that's basically P and Q and R. That's our first. And now we can build a second gate. Okay, we'll kind of extend our lines here. Okay, we can build a second gate, which will also be an AND. It's not a very good AND. Okay. All right, and now we need to figure out the inputs. Well, the inputs are P and not Q and R. Okay, so we're going to take our Q line and put a NOT on it and feed it in, and the other lines we can just feed in directly. Okay. And then finally, for a third end, okay, we have not Q and not R, so we're going to grab the R, put it through a NOT. We're going to take the Q, put it through a NOT, and we're going to take P directly and feed that into this. Okay, and then at the end, we're going to put an OR gate and combine all these different outputs. Okay, and that's our circuit S. Okay. So that is one way to build the circuit. It's very mechanical. It's a beautiful thing. But we can do better. Okay, so we know. Actually, let me ask first. Are there any questions before I move on? Okay, good enough. All right, so we can also go the other way about it. All right, so we can do let's say step 3 prime, okay, as an alternative to 3, right? And that's going to be simplify the logic. Okay, so we started with this expression, P and Q and R, okay, or P and not Q and R, or P and not Q and not R. Okay, how can we simplify it? Well, we know some rules for sort of algebra of these things, and so we can use the distributive property of end to simplify this. So we can, because P is in each of the substatements, so to speak, we can factor it out, okay? So we're gonna say that P is out, okay? And it's going to be an end. And now we can say Q and R, okay? Or the other factor, which would be not Q and R, and the final factor, which would be not Q and not R. Okay, so this is by distributive. Okay, now we can do this again, where we'll take P, and we can factor out not Q from the second set of parentheses. Okay, so we can say Q and R. We'll just copy this down. Okay, and then we can say or, and now we can combine the rest of the statement here. Okay, and factor out the not Q. Okay? So that's going to be not Q and R, or not R. Okay, also by distributive. Okay, so now if you look at R and not R, well, this is always going to be true. Okay, so we can basically drop all this and then get P and let's see, Q and R, or not Q. Okay, and that's our simplified expression. So now we can build a circuit for this. Okay, so we'll take this and we'll build a circuit here for it. Okay, so real quick, it's going to be P, Q, and R, and we can end these together. Okay, so that's our first inner parentheses here, Q and R. Okay, we can then get our not Q. Okay, and we can pass this to an OR gate. Okay, and then we can end this with P. Okay, so we basically went to 4 gates from this was 7 gates. Okay. And then if you do the truth table for this final statement here, okay, you will see that it's equivalent to this value of s, right? And maybe we should do that just to confirm. Okay. So let's see. Let me copy that. Actually, I'll put it up here. So we can have p and q and r, or not q. Okay. So let's look at a kind of a simplified way of doing the truth table. So first of all, for this whole thing to be true, p has to be true. Okay. So right away we can reject everything else on the bottom. All right. If p is false, the whole statement is false. We're done. Okay. So now the statement could be true if p is 1. What else do we know? Well, if the value of q is not or 0 and p is 1, then the statement is going to be true, right? Because this is going to be 1, and so we don't care what the value of r is. It's going to be p and true. Okay. So where we have q equal to 0, we can put a 1 here. Okay. And now for the rest of it, we can evaluate the value of q and r. Okay. And so here, q and r is going to be 0, and here it's going to be 1. And through these 16 very easy steps, you get to a simplified circuit and a simplified logical expression. Well, you get to a simplified logical expression that's equivalent. You can kind of test it first, and then if it is equivalent, you can then use it to build a simplified circuit. And that's actually kind of beautiful. Questions? I know somebody has a question, guys.
Yeah, would this be equivalent to saying P and parentheses not Q or R, close parentheses?
Will this be equivalent to P? What's after P?
And open parentheses, not Q or R, close parentheses?
Not Q or R, close parentheses. I don't know. Let's check.
What I ended up with.
Do you simplify it further? Am I missing a step of simplification?
I didn't really follow the process. I just kind of thought about the truth table.
Okay, so does it give the equivalent thing? Okay, so if P has to be true. Okay. Okay, so if Q is true, is false, we'll get this. And then or R. Yeah, I think it would be equivalent. So there might be, you might be able to show the equivalency of this and this, right? So there might be another step here in the transformation, right, to get to an even simpler circuit. Nice. Okay. Any other questions?
Are we doing K-maps?
No, I don't know what those are, so I'm going to say no. Okay.
Carnot maps.
Yeah, I'm not familiar with that. I should. What do you call them?
Karnaugh, Karnaugh. It's like another way to get to similar conclusions. It's a kind of grid format. But yeah, I was more just asking. That's something.
Yeah, no, I'm not. I'm actually not familiar with this. I'll look into this, but I mean, we're not doing them. So at this point, you guys should have everything you need to do the homework, and which is due Monday, and we'll kind of start on a new topic and a new homework starting Monday. So have a good weekend, and if there are any other questions, I'll kind of hang around for a second here.
You too.
But-
Thanks for teaching.
Yep, thank you.
Have a good weekend.
Thanks.